Systems of linear equations with two variables. A system of linear equations is when we have two or more linear equations. To determine if an ordered pair is a solution for the system, all we have to do is plug those coordinates into both equations and see if it comes out to be true. So in this first set of points, we have 1 and 2. So 1 is our x value, 2 is our y value, and we're going to plug them into both of these linear equations. So I'm plugging in 1 for x and 2 for y. And I'm going to solve it or simplify it and see if it comes out to be true. Well, 2 minus 6, that's -4, equals -4, and that's true, but it has to work in both equations for it to be a solution. So let's plug it into the second equation and see. All right, and we get 2 plus 2 equals 4, which is 4 equals 4, and that's true. So this is a solution to the system. Okay, so now let's try it with the other point. If I plug in 7, 6 into both equations, if I plug in 7 for x and 6 for y, that gives me 14 minus 18 equals -4. 14 minus 18 is -4, so -4 equals -4. Okay, so it works in the first equation. Let's see if it works in the second equation. And that gives me 14 plus 6 equals 4. Well, 14 plus 6 is 20, and that does not equal 4. So this is not a solution. So that's how we check to see if an ordered pair is a solution for the system. There are a couple of different ways that we can solve a system. One method is by using substitution. If we're going to use substitution to solve a system of equations, the first thing we want to do is isolate one of the variables. So we want to isolate whichever variable is easiest to isolate. So if I look at these two equations, the easiest variable to isolate would be this y in the second equation. That would be the easiest thing to get by itself. So that's what I'm going to do. In the second equation, I'm going to get y by itself by subtracting 2x from both sides. So that gives me y equals 1 minus 2x. And now I'm going to take what y is equal to. So y is equal to 1 minus 2x, and I'm going to substitute that into the other equation for y. Since y equals 1 minus 2x, I can replace y with what it's equal to. Okay, so if I take that and I plug it into the other equation, I get 3x plus 2 times 1 minus 2x. Anytime we substitute something in, we plug it in parentheses. Okay, so now that I've replaced y with what it's equal to, I need to simplify this equation. So I'm going to distribute the 2, and that gives me 3x plus 2 minus 4x equals 4. All right, so if I combine my like terms, 3x minus 4x, that's a negative x plus 2 equals 4. All right, so I'm going to subtract 2 from both sides, and that gives me negative x equals 2. Divide by -1, so x equals -2. Okay, so that gives me my x. Now I want to find what y is. So I can take this coordinate and plug it into either one of the equations that we started with. Well, I want to plug it into the second equation, and I'm going to plug it in right here since we already have y by itself, and y is what we're looking for. Okay, so if I take negative 2 and I plug it into that equation where the x is, that gives me y minus negative 2 times negative 2. All right, so that would be, I have to follow order of operations, so I want to multiply first. I'm going to multiply negative 2 times negative 2. That becomes a positive 4. So y equals 5. Okay, so the solution to my system is always going to be an ordered pair. So my ordered pair, that's the solution to my system, is negative 2, 5. That's the solution to my system. Okay, here's another system that we're going to solve using substitution. Again, we need to isolate a variable. Well, it doesn't matter which one of these equations we isolate a variable in, because either one, it would be easy to get y by itself. So I'm just going to go with the bottom one, and I'm going to subtract 3x from both sides to get the y by itself. So that gives me y equals 9 minus 3x. Okay, so now that I've gotten y by itself, y equals 9 minus 3x. So I'm going to take 9 minus 3x and substitute it into the other equation where the y is. Okay, so when I do that, I get negative 2x plus, and I'm substituting in 9, hold on, 9 minus 3x equals 4. Okay, so that's negative 2x plus 9 minus 3x equals 4. So if that sign in front of what I plugged in, if this had been a negative, we would need to distribute that negative sign. Since it's a positive, it doesn't matter. Okay, so now I want to combine like terms. So if I combine my negative 2 and my negative 3, that gives me a negative 5x plus 9 equals 4. All right, I'm going to subtract 9 from both sides. So that gives me a negative 5x equals negative 5 divided by negative 5. So x equals 1. Okay, we're not done because we're looking for the point where the two lines cross. That's the solution to a system, the point where the two lines cross. So that's what we're looking for. That's why our solution is always an ordered pair. It's the point where the two lines cross. Okay, so I have my x coordinate. I still need my y coordinate. Okay, so I'm going to take this 1 and plug it into, I could plug it into either equation and I would get the same answer. I'm going to plug it into the bottom equation where I've already solved for y, since I'm looking for y. So that gives me y equals 9 minus 3, and I'm plugging in 1 for x. So y equals 9 minus 3, because 3 times 1 is 3, or negative 3. And y equals 6. So my solution, my ordered pair that's my solution, is 1, 6. That's the point where those two lines cross. Another method that we can use for solving systems of equation is the addition method or the elimination method. Different books call them different things, but they mean the same thing. What we're going to do is we're going to add the two equations together and eliminate one of the variables. So that's why it's called either one of those. Well, sometimes we can just add the equations together and one of the variables automatically cancel out. Let's look at this system of equations here. If I were to add these two equations together, then when I add them together, remember there's understood ones in front of those x's. X plus x, or 1x plus 1x, is 2x. But a positive 2y and a negative 2y would cancel. And 5 plus 1 is 6. Okay, so I want to solve for x, so I'm going to divide by 2. So x equals 3. Now the last step in solving a system of equations using the addition method is the same as the substitution method. Once we get one of the variables, to find the other variable, we substitute that into one of the original equations to find the other variable. So I'm going to take this 3 that I got for x, and I'm going to substitute it into one of the original equations. It doesn't matter which one. I'm just going to go with the top equation. So if I take this 3 and I plug it in right here, and again, it doesn't matter which one, I could plug it into either one. If I plug it into that top equation, I get 3 for x plus 2y equals 5. Okay, so then I'm going to subtract 3 from both sides, and that gives me 2y equals 2, divide by 2, and y equals 1. So, again, my answer is always going to be an ordered pair, and my ordered pair for my solution is 3, 1. In the system that we just solved, when we added the two equations together, one of the variables automatically canceled. That doesn't always happen. So if I look at my two equations and I see that nothing is going to automatically cancel, then I need to multiply one or both of the equations by some number to get one of the variables to be additive inverses of each other. They need to have the same number with different signs. So always look at the smaller of the two and see if you can multiply that smaller number by something to get the bigger number. What I mean by that is, if I look at the y's, I ask myself, is there anything that I can multiply 3 by to get 5? Well, there's not. So let's look at the x's. If I look at the x's, is there anything I can multiply 2 by to get 4? And there is. If I multiply 2 times 2, I get 4. But I also want them to have opposite signs, so that means I would need to multiply by -2. Well, I can't just multiply one thing in the equation by some number. I have to multiply everything in the equation by the same number in order for it to be legal mathematically. Okay, so that's what I'm going to do. I'm going to multiply everything in this bottom equation times -2. So if I do that, I get -4x plus 6y equals -14. And then I'm going to just bring that top equation down and write it underneath here. So that gives me 4x plus 5y equals 3. And now when I add the two together, my x's cancel, and I get 11y equals -11. Divide by 11. So y equals -1. Okay, that's my y. I'm not done because I need to find the x. So I'm going to take that y and plug it into one of the original equations to get my x. It doesn't matter which one. I'm just going to go with the top one. So if I take this and I plug it in right here, then I have 4 x plus 5 times -1 equals 3. Alright, so 4x minus 5 equals 3. I'm going to add 5. So I get 4x equals 8. Divide by 4. So x equals 2. So the solution is 2, -1. Now, there are 3 possible types of solutions that we can get whenever we're solving a system of equations. Like I said, the solution to a system of equation means where the two lines cross each other. So what we're looking for is the point where the two lines cross. If I have two lines that cross at one point like this, then we have one solution. That point where they cross, this point right here, is the solution to the system. So there's one solution, and this is called a consistent system. But we could also have two lines that never cross each other. Well, we know that parallel lines never cross each other. So if they don't cross each other, then that means they don't have a solution. So this would be no solution. We could either write a 0 with a slash through it, or we could just write out that there's no solution. And a system like this is called an inconsistent system. And then the third possible type of solution that we could get is if we had two lines that are the same or two lines on top of each other. Okay, so if we have two lines on top of each other, then that means every point on both lines they're touching. So there's infinitely many solutions. Infinitely many solutions. And we call this a dependent system. So in a dependent system, I spelled that wrong, it's with an E. In a dependent system, the way that I think about it is it's the same line, there are two lines on top of each other, they depend on each other. So that's called a dependent system. Okay, so if they cross in one point, it's a consistent system. If they don't cross at all, that's an inconsistent system and there's no solution. If the two lines are the same, or the two lines are on top of each other, that's infinitely many solutions, and that's a dependent system. So let's see what that looks like in a system of equations. Okay, so here is a system of equations, and we can solve it using whichever method we want to. Since I don't see a variable without a coefficient on it, I think it'd probably be easier to use the addition method in this one. So if I were going to use the addition method, if I look at my variables, if I were to multiply everything in that top equation by a 2, then I would get things to cancel out. So if I multiply everything in this top equation times 2, let's see what I would get. I'm going to write it down underneath the second equation. So 2 times 5, that's 10x. 2 times negative 2y, that would be a negative 4y, equals 2 times 4, that's 8. So now if I add these two equations together, my x's cancel and my y's cancel. So I have 0 on this left side equals 15. Okay, is that a true statement? No, 0 does not equal 15. So if our variables cancel out and we have a false statement, that means that there's no solution. This would be an inconsistent system with no solution. All right, here's another one. This one I think would be easier to use substitution because we already have a variable by itself. The x is already by itself in the top equation. So I'm going to take what x is equal to, this, and substitute it into the other equation for x. Okay, so let me rewrite this. I have 5 and I'm substituting in 4y minus 8. Then I have minus 20y equals negative 40. All right, so I need to distribute the 5. That gives me 20y minus 40 minus 20y equals negative 40. Well, when I combine like terms, 20y and negative 20y, these two cancel out. And I'm left with negative 40 equals negative 40. Okay, again, my variables canceled out, but this time I have a true statement. So if I have a true statement, that means that we have infinitely many solutions, and we can just abbreviate infinitely many solutions. And this would be a dependent system because the two lines are the same.